Okay, welcome everybody to my session about SMB, Server Message Block, Microsoft Troubleshooting. My name is Rolf Leutert, and you may have realized already that I'm not Native American, not native English. I'm coming from Switzerland, running a small company over there, just 2 people, but fully specialized since 20 years in protocol analyzing. We do a lot of customer troubleshooting, we do trainings, and we started with the original sniffer from Network General many years back. Anybody knows sniffer? Oh, a lot of people with gray hairs. Yes, I switched then to Ethereal in 2006, just when the name change happened. We were the first award in Europe offering Wireshark courses, and that's up to date. We have a broad choice of courses from wireless to TCP to IPv6 to voice over IP, so all in that area. I tried to avoid so far to troubleshoot SMB. SMB is, according to discussion with other network specialists, it's not really the most likely protocol out there. And we always recommend that in our courses do troubleshooting for SMB up to TCP level, which is okay and works most of the time because TCP is the base of today's SMB. So SMB is called an application layer protocol. And in our trainings you learn that as a networker it's a must to have knowledge up to layer 4, up to TCP UDP, and with this knowledge you can do troubleshooting, you can do the most important decisions. Is the problem on the server side, on the network side, or on the client side? And this is still true. And we will still teach it in our courses. This is the must part. Everything above is the optional part. So we are talking about optional parts today, SMB, because you actually can prove with TCP knowledge if the network is okay or not. And that in most cases that is enough. But there are some cases where the customer would like to know more. And that was actually the case 2 months ago when I was contacted by a large customer in Switzerland. He was in clinch with Microsoft about a problem in his network. The SMB session keeps releasing, crashing, and they were sending back and forth traces before I came into the game. And Microsoft, with his SMB protocol, insisted that the problem is on TCP layer or on the network below because it's losing packet. And I had to look into it, and I cannot say you at this time how it will come out because we are still in the clinch, but I can try to show you the situation we are in. And that was actually the occasion to dig a little bit more into SMB. I did it many, many years back, but I kept forgetting, and it was very different at that time. So I started to look a little bit closer, especially at the newer version. There's an SMB version 2 and 3, and it's much more straightforward than the earlier ones. So we will look into these, and we'll learn like a lot of things. When you look a little bit closer into it, they are not that bad as you may think at first sight. I also have the trace file for you here on a Shark. I will start swimming around. If you have your notebook with you or something else, you may copy the files. Otherwise, you can send me an email if you're interested, and I will send you the file. Herbert, could you start this Shark going around? Okay. I mentioned already server message block Microsoft's client-server protocol, initially invented by IBM many years back, 83, so it's 30 years in age, and it's still in use, but it has done many changes. It's completely different from the first one. Comparing to TCP, which is even older, TCP is still the same. And that's really a big difference between this. Of course, we are one layer higher, I mentioned already, but still this protocol is very different from what it was the first day. It actually was invented for small work groups, not for routable, not for huge networks. It was based on this NetBIOS, NetBEUI, you may remember. It was working with names, so no addresses. Every station had a unique name, and services were found and searched by names. So it used a lot of broadcast. That's what it was famous for. That's why it was not also usable in large areas, because the broadcasts they were using were just swamming all the network. So initially it was the idea not using it behind a subnet broadcast area. So that was the initial idea, but it didn't scale, of course, because soon this TCP IP came into the game and was able to make large networks with routers and keeping broadcasts local. So they had to change from names to addresses or to IP addresses, and we'll look into how this worked. There's also another name around for this protocol side. It's called CIFS, so it's interchangeable. You hear both names represent the same kind of protocol. Microsoft took over and made this to their server client protocol. But there's also non-Microsoft implementations available, open source implementations for Unix world. So if you have a Unix server and you want access files from a Windows workstation, you may use Samba. That's just for completeness. We are looking into Microsoft's implementation here in this presentation. So let's look a little bit back at the moment when they started to remove NetBEUI, the non-routable protocol, when they started to put SMB on top of TCP. So what they did, they reserved a few ports, which you can see here on the slides, and you will still find these ports used in your network, even so they are not the latest release. I will show you in a minute. But if you see port 37 and 38 on your network and 39, then you probably have this so-called MPT implementation, NetBIOS over UDP and TCP. We are looking at these different services right in a minute. And that's where the first implementation started. But today, the preferred way of using SMB is so-called NAKed over TCP using port 445. So UDP is not in use anymore. It's running through TCP, which makes the conversation, of course, reliable, because SMB then is using all the TCP functions with acknowledges and retransmissions and all TCP is offering. So this is the way to go. If you have your port 445 in your trace files, then you are on the latest implementation. So this is one thing how SMB is implemented over TCP. But there are also different TCP SMB versions, which had nothing to do with the implementation. Don't mix this up. So we will look at this in a minute. So the first implementation was with using these 3 ports and using different services. The initial NetBIOS, as I mentioned already, was not routable. It was searching name with broadcasts in the network. So a lot of these broadcasts, I have a screenshot here, were sent out. You see the 255 here at the end for NetBIOS queries, for NetBIOS announcements. So a lot of subnet broadcasts have been used, and they have been used to announce own names, but also find names from services, printer services, file services. They all have been found or searched for with broadcast. That's exactly what we didn't like too much about the protocol, because broadcasts, first of all, they produce load on the wires and on the switches. Second, they interrupt all stations, because a broadcast must be processed by every single station, which takes resources from the station. Later on, this was improved with a so-called WINS server, kind of DNS way of having a central directory about names. So this was the first step of getting rid of broadcast. So the WINS server could have been even behind a router. So what you have to configure on the client, what you had to configure on the client was the WINS IP address, and then it was not broadcasting, it was contacting this server to resolve a name into an IP address. So this was a slight improvement before they finally then introduced DNS like we know it from other TCP. So the name service using port 137 was based on UDP. Of course, every broadcast is based on UDP. The other service, 138, so-called datagram service, also based on UDP. This is unacknowledged message based on UDP, used for unicast and multicast, for browser election and so on. And then finally, when a session was built up, they used port 139 on TCP to access a file, read or write, and so on. So this was the implementation, and you may have still this way, but this is not the latest one, as we are seeing in a minute. Wireshark decodes perfectly these ports, by telling you the port number, and you know the possibility of having names instead of numbers. So NetBIOS name service here decoded port 137. The same is true for the datagram service, 138 here. So these are browser announcements, as you can see up here, and other announcements. They are using datagram service to the broadcast address. You see here MAC broadcast, and you see also the IP broadcast here. So that's to confirm what we learned already. And here the session service then based on TCP. You see here the TCP layer below and the port then 139. So this is the 3 port. Let me go back to this chart, the 3 ports which are used in previous implementation. But the trend is going in another direction. The trend is going to SMB naked, called naked over TCP, using port 445 only. So no UDP messages anymore. We don't need them anymore because all the stuff with names resolution has been removed from SMB and is done through DNS. As normal DNS resolver we know from the IP and other protocols. So there's nothing left from this old name announcements or searching process. So this is since Windows 2000 and XP and Samba appropriate version is implemented that way. So you hardly ever should find older implementation we just saw on the previous slide. But you never know, and it may be a reason to tell the customer to upgrade to newer version. So here you see then an implementation, of course, Wireshark again shows this here perfectly decoded. In TCP session, the source port randomly selected by the client, and the destination port then Microsoft 445. Microsoft Directory Service is what the DS stands for. So this is how it's implemented on top of TCP. This is the first step to recognize. You may have to look in. The second is what SMB version is used in your environment. And here we have again quite a choice of different languages and dialects. So we have kind of main languages here, SMB 1, 2, or 3. Actually, it's not called 1 because it didn't have a number at that time, but it's called SMB. And we have additional dialects. So that means like subsets of the more than 10 different dialects are available for the first SMB version. They are quite complex. You can see here the number of pages I found from Microsoft, 782 pages, just this file here describing the different dialects and SMB. Here we have 400 and odd pages. So there's a lot of information available, but not from different sources. And this is something which I found out to be very hard. There is not one real book around out there which tells you in a readable form about the different versions. I found a book, I show you the link in a minute, but it does not cover the latest version of SMB, and then it's more or less not usable. So that is really surprising, because every company having Microsoft Windows Server in use will have this protocol on the network. And it's probably, I would say, the least documented protocol available. So you find thousands of books about TCP, you hardly find anything about this protocol. So these links are valuable, but the readability is not really like a book where it's explained in more comment. It's a lot of references to other places, so if you start like an RFC, it's not really the way to work through. Anyway, we have to live with it, so here are the links which will give you more information. So SMB1 has more than 10 different dialects available. We are quickly looking what kind of dialects are available. Then SMB2 has been completely reworked. It's much easier, less chatty. It has been improved dramatically. So we will focus only on these versions here throughout this presentation, because this is the newer one and this is the way to go. It's available since Vista, Windows Vista and up, has performance improvements and a lot of other functions. We will look at some of them. Reconnection of the network outages, one nice thing. Then was a version 2.0.2.1, again improvement in latency, MTU support, and the latest one, which also have traces of is SMB version 3, only available with Windows 8 up and Windows Server 2002. There's also a big mess in the naming if you look on the internet, because initially version 3 was named 2.2, so you find both, but it has been renamed. Version 2.2 has become version 3. Wireshark will decode all of them, and we will see there is a minor difference between 2 and 3. It's mainly functionality which has been improved, and less frame and headers, but the difference between here and here is huge. We will see it in a minute, what more details have been improved. So SMB2 has reduced the number of commands from over 100 in first SMB version to just 19. Still a lot for file reading and writing, but comparing to more than 100 in the first SMB version, it makes life much easier. It has been improved in several details. We will look at one important one. It's called durable file handle. So SMB2 now is able to even handle short network outages. So that means if you have version 1, if a network fails and the TCP session is released, you must set up a completely new session, and you must issue the new read command, and you must start at the beginning of the file and things like this. This is not the case anymore from SMB2. We will see a trace file. It is even able to continue with the file transfer at the point the link was broken. This is just one of a lot of improvement, but this is one we can see with the Wireshark. So that's why I would like to show you this one. Anyway, we can say that the intention of Microsoft is to push the SMB protocol again, to relaunch it again, especially also for server environment. They lost field here towards other protocols like NFS, and they would like to gain this back. So that's where they made a lot of improvement, and the effect is that quite a few vendors listed here already support or have announced support for version 3.0. So it looks like Microsoft is gaining ground again here on this part. So here a list of the details. I just copied from the internet. I don't understand it all myself. It's too much operating system oriented. I'm a networker, so but as I said, some of them are really interesting to look at with the Wireshark, the durable file handle, which I just explained, and other things like large MTU support. These are the things which you really can analyze with your Wireshark. So this is just for your reference to see that there has been quite some new functions in here. So how do you guarantee backward compatibility if you have so many versions of protocols? And this is something they solved with negotiation at the beginning of a session, and you of course can follow this process. It's quite interesting to see and to notice if the process is successful. So this is a table which shows which has to talk to which with which version. So for example, only a Windows 8 client can use version 3 talking to a Windows 2.12 server. If he's talking to an older server, it will negotiate down to SMB1. And this process is interesting to see, and that's why I made files here which we are going to look at in right a minute. So Wireshark differentiates between SMB and SMB, sorry, it's a little bit sensitive here, between SMB and SMB2. You can see here. So if there is no number here, then it's the SMB1, or as I said, the pre-version 2, if you like. If it says SMB2, it still could be SMB3 also, because, as I mentioned, there is no framing difference between 3 and 2, so you won't see a 3 here, but you will find out whether the two stations are going to use 3 or 2.1 or 2.0. And that's what we are looking at right now. So the first frame you may see going out from a client, the session build-up is the same here as with TCP. It's always initiated by a client. So the source in the first frame is called the client by definition. So the 229 here is the client, and the 207 is the server. By definition, that's the role. And what the client does here, it offers a number of dialects. So these are different dialects which he is supporting. Let's look at them a little bit closer, and you'll find a lot of information for them. You remember the workgroup 31A, very old stuff. So it still supports this, and it even supports, version 2, 2002, and then here a 2 with question marks. What does that mean? A 2 with question mark means that this is a so-called multi-protocol offer. It's telling the server, I offer you different version 1 dialects, I offer you a specific version 2, and if you have other version 2 dialects, then please respond. Okay, that's the first frame going out. Let's go back, and this is a so-called negotiate protocol request, you see here. And interesting now is that already the answer from the server is coming back with an SMB2. So the server realized, because he looked into the offer here, he realized that the client is able to talk version 2. So the negotiate protocol response already comes back with version 2. Let's look at this on the next slide. Version 2, let's see what the server is offering in the response. So it's offering a dialect 2FF. Can you read it at the back, or can you read it now? Okay. It's offering a dialect 2FF, which again is kind of non-defined version. It says, yes, you can talk to me with any version 2. So let's get rid of 1 with all these dialects. Let's talk version 2. So let's look how this dialogue goes on. The client now repeats the negotiation protocol request by sending another request, this time in version 2. And let's look what here is inside that. That's on the next slide. So now you see that the client is offering version 202, 2.1.0, or even version 3, which is SMB3. So this must be a Windows 8 client or a server 2012. Actually, In this case, it's a Windows 8 client. Only they are capable of version 3. You remember the chart which I showed to you. So let's look what the server responds now. And once again, don't get confused. If it says SMB2 dialect 300, it's actually SMB3. That's how it's defined these days, but we will see that Wireshark still would say SMB2. So let's look what the server in the next frame is replying in the response, and it's a 2012 server, so it comes back and says, okay, let's go to the top, let's take the 3. So if we look at back at the matrix we just had, we are actually in that corner now. We have both the support of the latest protocol on both sides. So this is what you can look at very easy. This is a clear text, more or less, what happens here. And I always recommend also in our courses, we always recommend look at it as long as it's working, right? Don't start analyzing it when you have a problem, because then you never know what is the reference. So even you don't understand all the details, make a trace of your normal situation, store it and use it as a reference later. You cannot understand all the details. It's impossible. There's so much details in these headers. We are going to look at some of them only. But there is no need to really understand everything, as you may be able to find differences just by comparing traces. So here another screenshot of all the dialects available in version 1 with some details and the link. So as your reference, you see here different improvements in every dialect again. So this is a long story with a lot of more details. And then here the versions which we are just looked at. Version 300 actually is SMB3. And that's how we saw the dialogue will go on. We start with an SMB negotiate and continue with an SMB2 negotiate. So we will focus on commands on version 2 only. No, will not spend any time on version 1. It's just too many different commands. So Wireshark can assist you here a lot by showing these dialogues, and as you know, Wireshark has some excellent feature to add columns, specific columns, and that's what I would like to do first. I would like to show you which details out of the headers are really helpful in analyzing SMB. So first we create a new profile. Anybody knows how to work with profiles? Okay, very useful feature of Wireshark. So I have a lot of profiles available. If you click down here in the field, you see a lot of profiles. I have a profile for more or less every different topology: voice over IP, virtual routers, redundancy protocol, SCTP, RTP. That's really very useful. Dual interfaces. You may know that you have a possibility now to capture from multiple interfaces, diameter protocol, and so on. And I, of course, also have one for SMB, but I will not use that one. I will create a new one, so show you how this profile is filled in. So you can do it from down here with right-click, but it's more visible if I do it from up here. Go down to configuration profile and just say I'd like the new one. I call it SMB. For those who don't use profiles yet, profiles is a collection of filters, is a collection of coloring rules, it's a collection of whatever you change in your display. So if you add columns, which we are going to do right in a minute, this column is in this profile. Whenever you open this profile, you have this column back. And of course, columns are dependent on what you analyze. In the wireless column, in the wireless profile, which you will see in my presentation on Tuesday, you will have columns about signal strengths, channel number, frame speeds. These columns are useless in SMB, right? They would be empty and just consume space. So using different profiles for different protocols makes really sense. And I just started a new profile, but I didn't change anything. A button you should use frequently is this one here, the Resize all columns. You see here these overlapping addresses. Whenever you change something, filtering or so, use this button here, Resize column. It is very helpful. So you may see down here, I have a new profile called SMB. And what I would like to do, I would like to make first a filter for SMB so that I can filter out any protocol. You must make a filter for SMB and SMB2 because there are different protocols. So you must say SMB or SMB2 in order to get both protocols visible. So pressing apply, I see that in this trace file only SMB1 or SMB native is available. And I make a quick button, a filter button with this save, also a quite new feature, but very useful. If you press save here, it will create a filter button with this filter, and I just call it any SMB. So whenever I open a trace file, I just can press this button and it will filter to any SMB traffic. So that's easy. And it's already in the profile, so you don't have to store anything. It's in the profile and saved. So let's go back to our trace here. Which I would like to modify in a way that you see a so-called sequence number and an NT status message column. So I open now a new trace file with SMB2 because the one I have right now is SMB1 or native. So I open a new trace file. It's called SMB33 Connect. Let's open that one. You should have it also in your copy. Okay. The button has been applied already. And we see here SMB, the process which we just looked at. And then we see more packets here, session setup, tree connect. We will discuss this. Packets in the middle, I/O control, request, response, create. There are 19 different of these, and we will go through the important one. But first of all, we would like to assign or open an additional column because not always responses are following requests immediately, like here. So sometimes we will see that multiple requests have been sent out, and then it may be not that easy anymore to assign responses to requests. And therefore we have in the commands, we have a valuable sequence number in the header. And that's the one we are going to search for and use it as a column. So here it is, command sequence number 7. right-click, apply as column, makes it another column. I preferably use the align center option, have it more readable, and what I normally do is I shorten the title so that it doesn't use edit column detail, so it doesn't use the full size. I just say sequence number. I know what the rest is, or sequence is even enough. So I know this is the sequence number. Now what you can see is that except the first SMB, because this didn't have the sequence number yet, the SMB native, but the first SMB starts with the 0. That's unusual. That's a response to this one. That's unusual. We send back an SMB2 to a native SMB. This is normally not this is the only situation where this happens. But then we see that every command, every request has a number, and the appropriate response has the same number. So we can easily assign now responses to requests. I said here it's easy because they are in order, but here they are not in order. You can see we have 2 requests, 6 and 7, and then 2 responses. So you need this additional sequence number to be able to follow the dialogue. You see here you can even combine 2 requests in 1 frame, and then the answer comes back in 2 frames. So there are a lot of varieties we will see. How much time I've left? And I've 4? Oh. Half hour. Okay. I tend to lose myself in details, so Wireshark is a tool for details, so there are a lot of interesting details. The next column we are inserting is the status, NT-status message. This comes with every response. And obviously status success is a good message, but there are others. So we would like not only to be able to assign a response, but we would also like to be able to look what kind of response it is. So let's do this. Let's just select any response and find the status. Here it is. Same procedure. Apply as column. Adjust columns, and you see that all the different, let's make this a little bit smaller here, okay, all the replies, all the responses have a success message or something else. I will give you a list of all these status messages, of course, but the next filter is now obvious. Let's do a filter on non-success messages, because these are obviously the ones we are interested in normally, right? Because everything is successful, then customer would probably not complain. So let's make another filter and let's make a button on it on status success. So what you can do is you can here use the success message as the sample, prepare a filter, so it copies the message SMB. You hardly can read it behind. I make it larger. So what it does actually, it copies the field name and the value. And the value 0 is obviously the value for OK, for status success. So what we do here, we change this, cursor. We change this to bigger than, or larger than, or how you say, larger than. That means we are interested in everything which is not successful. Let's see if our filter is working. Apply. So we should have messages only not successful. It seems to more processing required. That is at the beginning, at the session setup, it asked for identification. File system driver required, object not found, and so on. And let's make a button, a quick filter button out of this by pressing here the save button and come on, and call it maybe not okay, not okay, or whatever you want it. And it's in my profile already, so I go back to all and to not okay in a minute. That's how we are prepared now for analyzing SMB. There is, some people may ask, isn't there something like a file handle? Yeah, there is something like a file handle, which is a reference to a file opening, but I find out it's not usable because it's not referred in the responses. So whenever you open a file, and we are going to look at it in a minute, whenever you open a file, you get a file handle, which is a long number, from the server telling the client whenever you make a transaction, use this file handle. So the client is using the file handle, but in the reply from the server, the file handle field is not there. So it's really not very useful, so that's why I suppressed it here, but you may use it if you want, but I found out it's not of great value. In other protocols, they have to you work more with these file handles because they are consistently used and in responses and in requests, but here this is not the case. Anyway, this is the not okay button which we just created. So the most frequently used or seen messages are quite understandable. We've just seen the negotiate protocol, setup account, the tree connect we are going to see, the create, the I/O control, read, write, close, tree disconnect, and log off. There are much more. As I said, there are 19, and you will see a complete list, but these are the most one, and they are actually quite understandable, like we will see in a minute. So, for example, if you, after the session setup, after the negotiation, you start with the session setup. You see here, again, the references. And then you connect with a so-called share. This is the inter-process communication share, how it's called, IPC share, with this IPC $sign. So this is the share which is used to authenticate or bring a list of resources which are shareable and things like this. So this is the most common share you will see. So the first thing the client does, it connects with this share, with the IPC share, and it will get a tree connect response down here which says, okay, you are now connected. So you can easily test this with a command. Just open your command prompt and enter netuse, and this is if you share a drive on a remote server. So X will be your local drive number. You just enter the IP address of your server, and you may enter username and password if required. And this is exactly what you will see in the background. So this is the trace which followed this command. And then you will see some I/O control messages. They are very specific. So they are device specific, whatever that means. It says here that it's some negotiation between file access and things like this. So you even see some errors which obviously are not kind of hindering to access the file. So this is something which again is very confusing. You may see error in SMB, but they may not have effect on the function, on the operation. So that's why I say it's important to look at it under normal. So this is a normal file access. It worked, it opened, but still you have some error message. So it looks for some things which obviously are not really necessary. Here again you see that 2 requests may be sent in immediate order, and then the responses come back, and here again you need the sequence number to reference. And then there is another feature. You can combine multiple SMB requests and responses in one frame. They are called compounded requests and compounded responses. You easily will see it because Wireshark will show you here this frame has 2 sequence numbers, 17 and 18. So it will also show you both requests. The first one is a get info. In this case, the second one too. It may be a different one. And these commands are combined in a way that, of course, we have only one TCP header. We have the remaining part of the NetBIOS session service header. This is always present. This is a leftover from NetBIOS. Even so, it's called naked SMB over TCP. This part is always there. And then you have multiple of these requests or these infos. How does the receiver now realize that there are multiple requests to process? This is done via an offset field in the first header. In the first header, it is an offset field, and if this offset field is other than 0, it says more to follow. And that's what I would like to show you on the live Wireshark, because it took me a while to find out how this offset is calculated. So let me get another file. It's not an SMB 3 again, it's an SMB 2. Okay. Here we go. 1718. We have 2 SMB commands. And if we go into the first header, and if we go down a little bit, you find a chain offset value. And if this is non-zero, it means after a number of bytes, another SMB header is following. You can even chain more than 2 headers. The rule says as soon as the chain offset is 0, this is the last header. So let's check in the last header the chain offset, and it is 0. Okay? Now how you become here this offset, it says 70, and actually you just take the 70, and if you calculate this from hex to binary or to decimal, then it ends up in 112 bytes, which is exactly the difference between the first header and the second header. So it says with what offset the second header follows. This seems to work okay, but then I found an exception, and I found the exception with the customer I was talking before, And there is obviously another way of combining messages in one frame. And I, up to now, don't have the confirmation from Microsoft that this way is legal or not. Yes, the 7.0, if you calculate the 7.0, if you calculate it to hex, it gives you 112 bytes. That's another question. Why do they have such a long field? You can never have an offset longer than the, maybe you can have an offset longer than the frame length, yes? Maybe. I didn't check. A good question, why is this field here, this offset field, it's actually quite long. As you see, where is it? I'm too close now. Here is it. Ah, here. Okay. It's actually 4 bytes. Huh? 4 bytes. 4 bytes gives you 200, if it's continuous, gives you 4 billions, right? I have no explanation for that. Maybe they have some spare bytes or whatever. No, I think there is a reason, but I didn't find out why it's that long. Anyway, but the point is, I found a different implementation of this compounded request, and this was confusing me. Remember here what I said. You see one NetBIOS header, and then the 2 messages, the first with an offset. But when I looked at the trace file from the customer, I find another way of implementation. I found the way down here with 2 NetBIOS header. And the difference here is now the offset is 0 here. And here too. Here anyway, but here also here. So I didn't find out how the receiver of this message even can find out there is something more following. How does it do it? Because there is no indication in the first part that there is something following. Yes? I cannot hear you. Mag? You mean magnify? Or what? On the trace file. Here, the first header has only 1 NetBIOS, and the second has 2. No, this is a screenshot. I cannot magnify the header. I don't have this file available. It's from a customer. You don't have it either. But I looked into it. The offset is 0. I can confirm you. The offset is 0 in both headers. So for me, I didn't find out whether this is a legal implementation or not. We will still negotiate it with. Obviously, we've seen some answer coming back to this kind of compound, so we assume that it is. But in the specs, you only see about the first one. Yes?
The compound one, they might be using an exception of transmission and using another one of the fields to indicate.
You think that there is some other indication?
Yeah, that when they transmit in compound mode, they use another field.
Maybe, but in the specs it clearly says a compound frame must be marked by the offset. That's the field they use for that. So this is a question mark which I cannot answer so far. It seems to work, but it does not say anything about this in the specs, and it left a lot of question mark. Yes? Yes, yes. How does he? Yes. Actually, what I found out is that let's go back to the Wireshark, that every SMB header starts with an SMB in clear text. You see here? So maybe it's looking for SMB. So every SMB header starts with the clear 3 digits SMB. So if I go to the header here, you see this is the SMB, and if I go down to the next header, then you see another SMB. So I don't know if it's scanning for this pattern or. So that's I cannot answer at the moment. Yes. If I have more errors? No, as I said, I realized that the dialogue is working either way of compounded. The answers coming back were okay. So I assume that it is a different way of implementation, and it seems to work. I just wondered why I didn't find it described in any specs. And I wonder if every client and server can handle it or not. I must leave that open for the moment.
What I'm saying is, in our presentation, we do have scenarios where you actually found that it frames the SMB problem problems with SMB.
Yeah. No, I don't, because this file is from the customer, I told you, and I didn't see any other implementation like this so far. This is the first and only.
So one error is that it did not affect.
Yes. But when you're looking for error, you find things like this, right? And then you think, oh, I got it. And then you further investigate, and then you find out, okay, it's different, but obviously the client or the server can handle it, and then you just leave it open for the moment. And I hope we have another meeting with Microsoft next month with the customer involved, and I hope they have some answer ready for that one. We sent them the trace file. They didn't answer to that. They just said this has nothing to do with the problem. Which we couldn't prove the opposite, so it may be right that it has nothing to do with the problem, but it's still different. Still, yes. The problem, I'm just coming back to the real problem, yes. So, what I would like, 15 minutes left, right? Okay, I don't know the schedule. Anyway. I come back to the real problem with the customer, which is not solved yet, but we have some indication. So let's look to read and write commands. When you read or write the file, SMB again has some special way of doing it. It reads blockwise through the file. So it says here read request, a block of 65,000 odd bytes at offset 0. And then the frames are delivered in TCP, of course, so you see a lot of TCP packets coming without SMB header up to this number of bytes here. And then the next read request, or here even just in a row, you see the next read request going out with the next offset. So that's how it works. We are reading through the file and increasing the offset. At the end, obviously, the client knows how long the file is, so the last request here is not full block size anymore, because obviously he calculates and finds out that these are the remaining bytes. And then the frames come back here, and this is already a condensed view, because in real it would look different, because we would have a lot of TCP frames in between. I'll show you this on live trace again. So let's open the file read remote and look how this is really happening. So I clear my filter and I go to my frame here. Oh, a little bit struggled. Let me find the place here. Obviously, TCP checksum is validated here, so let's put that out. Okay, here we go. And let's turn off the Wireshark feature of reassembling first, and then how we see how it's really going on. Okay. Ready now? So here you see a read request. No, let's go a little bit down. It's more visible here. Here you see a read request, 65,000 at offset 0, and immediately afterwards a read request, 65,000 at 65,000. So these are two read requests, 1059 and 1060. And then you receive an answer, SMB, status success. So this is the answer to this first request. And now you see the file delivered in full-size frames here, in between acknowledges. So it has to deliver the 65K now in segmented frames. There is no other way. And that's how Wireshark is displaying this without assembling. Now you can say, Wireshark, please assemble this answer into one answer. And this is done by selecting TCP, and that's quite a handy feature. Right-click, protocol preferences, allow sub-dissector to reassemble TCP stream. So I select that one, and now it looks different. What you find out is that the read request is up here, but the read answer is now at the read response is now at the last frame. So that's different. What Wireshark does, it collects all the answers, all the frames which belong together into a stream, 45 reassembled TCP, and it also has now in this frame the full file, also 65. So if you go down now, here are all the assembled frames which has been previously sent. So these are, depending on what you want to see, you can select either way of display, either assembled or not. But the dialog is still the same. I go back and make my filter. You see read requests here, 61, 62, replies, and so on. That's how it's reading through the file. And what I would like to show now is the possibility of durable file handle. And that's where we came into. No, it must not be, the answers must not be in order. Here they are in order. You have 61 and 62, 61 and 62. Is that what you're asking? Yes, they must not, but here on the slide they are. But they must not, may not. Would that be? Okay. Sorry for that. Yes, you're right. I mixed. You know that in English and German, may and must are false friends. like silicon and silicium.
In the problem that you were mentioning about the company that you are troubleshooting, are you able to share what is the statement of the problem that they are facing?
Yeah, the problem is that the file transfer, which I write here, is breaking down regularly in regular intervals before it's finished. So what they do, they read multiple files, each 10 megabytes, and here we see the read request. This is the trace file again from the customer. No, the next one is, sorry. This is trace file from the customer again. So what they do, they read multiple files. Each file is 10 mega. The file numbers go up to 23 and so on, and in regular interval it just breaks and stops completely. And we have TCP drops. That's confirmed. Quite a bit of TCP drops because they have speed conversions from 1 gig to 100 meg. And this is always difficult, right? And what we see here is that a session handle, durable session handle. What you see here, and this is before the break, you may see it. This is a read request at a certain offset. Remember this number here, 5,575,60 at a file with the blah 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 name, you don't need to remember this, 23. Then the session went down because of TCP retransmissions. Finally the session was released by SMB and it was built up again with negotiate. There is a completely new session here. This is in the same trace file, no fake. In the same trace file, just further down. And now you see, if you go further down, you see the same request at the same offset for the same file. So before this read request could have been delivered, the session has broken, and we see here that it continues at the same offset, and that's what they call durable file handle, which is very handy, but obviously we still had a problem. And the problem which they had is that if they had this breakdown in one of the transfer, after an odd number of 23, the conversation breaks completely. So it's always a multiple of 23, they found out. So if it's transferring between 36 and whatever, then it's failing at 46. Strange numbers. And this is confirmed by Microsoft. So this durable file handle, which obviously seems to work at some point, still triggers another problem which they didn't accept. No, they accepted more or less, but they don't have the solution. And which led to the situation that the file transfer still stopped at the point where it was not finished yet. So, yeah, we ran out of time. I just wanted to show you here, TCP analysis is okay and is still good and it's still the basis for everything, but sometimes it may be required to look more into the application protocol, and here we have a case. We know that we are losing frame, but TCP is able to handle lost frame. And we can see here that even SMB is able to handle lost frame, but obviously not under every circumstance. And we are still working on this, and it was just the occasion to look a little bit more into Wireshark and what Wireshark can do for you. So the last minutes, I must go real quick. SMB has other features like if you go here to statistics and response times, and if you go down to SMB, it gives you a list of all commands which have been found in the trace file. And it gives you an average response time of these commands. You even can make a right-click filter on any of these commands, and it filters out immediately all read commands and things like this. So this is quite handy also that yes. You also can export objects, SMB objects. If you go to this upper corner here, export objects, SMB, and he will give you a list of all found objects if you make a read. And you can now even say you should save this, this object, and then you can open it. So here it's a Wireshark JPEG picture. You could open it afterwards like a normal file. So it's just collecting all the data he's recognized in the read or write command, and is presenting this to store. Yeah, okay, this is more for your reference. All the 19 SMB2 commands, all the dozens of status non-OK messages. Again, we made a filter on that. Some are understandable, no more files, no such file, access denied. Most of them are more or less clear text, so there is no further explanation required. And again, very little literature available. And that's the book I found, but again, unfortunately, not covering version 2 and 3. So you must more or less keep to Microsoft specs here, which you found some links in the presentation. Okay, sorry for the hurry, but it is a huge topic, and I try to pick out some useful thing and encourage you to dig into yourself if required. Any questions? Okay, thank you very much.